All right, in this video I want to take a look at higher order Taylor polynomials. And in doing so I'm going to just go back and essentially start from the beginning, just to remind you what we've done and to see how each step is just doing the same thing over and over again. Right? That we started off with essentially just the statement of the fundamental theorem of calculus part 1, and that if you integrate f prime of t dt from x to b, you're going to get f of x minus f of b, and then I move this over here. So this was our constant approximation, that if we're approximating the function f of x at x equals b, so figure out what f of b is, and that's going to be my approximation for every other x. This wasn't a very good approximation, but that's what we called it, right, a couple of videos ago. Anyway, this part right here is the constant approximation, and this is what we use to get the associated error with that constant approximation. Where you say, hey, if I could get a bound on that first derivative, then I could just consider that a constant, pull it out, and just do the integral of dt, which would just be x minus b. And so that's what the error formula here is. It's m times x minus b, where m is some upper bound on the size of the first derivative there, the absolute value of the first derivative, on the interval between x and b. Right. Then, to get the linear approximation, we said, all right, let's integrate by parts. So we took this thing, and I let's see, integration by parts, I start with u and dv. So the f prime of t is the u, and the dt is the dv. So take the derivative of u to get du, so that would be the second derivative of f. And then we integrate dt to get t plus a constant. And here's a little bit of creativity. Someone was pretty clever in doing this. The variable here is t, so x is just a constant with respect to this integration, and so we're just going to call it x minus t. It really doesn't matter. It comes out in the wash, whether you have the plus c or not there, but in this case it'll make a difference to us, so we put it in. So let's see. So then the f of b was already there. So integration by parts, I have the u times v, that's out in front, minus the integral of v du. But since this is a definite integral, I have to evaluate that u times v part between my starting and ending point, b and x. And so I plug the x in for t here, and the x minus x is going to be a 0, so that's just going to be a 0. And then plugging the b in for the t there and there, and we get that. So anyway, what happens between here and the next line? So this part goes away. And this minus sign, I just distributed into the b minus x and turned it into an x minus b. So that became a plus sign. And likewise, this minus sign, I'm going to distribute it into this t minus x and make it an x minus t. And so what I have here, f of x equals f of b plus f prime of b times x minus b. That's the linear approximation, plus the rest of it, which is what we get our error formula for the linear approximation from. This case, we say, hey, if I had a bound, if I knew that f double prime was no bigger than some number, then I can just treat the whole thing as that number, pull it out, and just integrate the x minus t. Well, the x minus t is going to integrate to well, it's going to be an x minus t squared over 2. There's a minus sign in there, but then you're subtracting when you plug the x and the b in. Anyway, it comes out to essentially x minus b squared over 2, right? You get that linear. In t, it's going to go to a quadratic in t, but then the t gets replaced by the b. It also gets replaced by the x, but when you replace the x in the you're going to have an x minus x, and you won't see that term. Anyway, this is the size of that integral times however big the second derivative might be. Okay, so it looks very much the same as the first, except that m here is an upper bound on the next derivative, and you've integrated that part of it. The x minus b integrates to x minus b squared over 2. So then we say, all right, let's do the quadratic approximation. Again, we've already done all of this, and we say, let's integrate by parts. So I'm looking at this thing right here, and the f double prime is my u, and the x minus t dt is my dv. Take the derivative to get the du. That's the third derivative of f, and you integrate with respect to t here. There's a minus sign that pops in because there's a minus in front of the t. So with the u substitution there, you get minus x minus t squared over 2. And then same thing. It's this stuff was already there. And then I've got u times v, so this times that, evaluated between t equals b and t equals x minus the integral of v du. And plugging the x in here gives me a 0. Plugging the b in gives me a, I'm plugging in for t. This is minus, and I'm subtracting when I plug the b in, so the minus minus becomes a plus. That's why this term here is a plus. And then this minus minus becomes a plus, and we just get this integral. So again, we get to the point where we've got the quadratic approximation right here, plus the rest of what the function needs in order to actually be equal to f of x. So this is where the error is, and you can estimate that error by getting an estimate on the third derivative. So m is an upper bound on the third derivative, and then you just integrate that. Again, plugging the x and the b. You get zeros when you plug the x in. You get x minus b when you plug b in for t. And you just end up with this cubed, x minus b cubed over 3 factorial. 3 factorial, of course, is 3 times 2 times 1, right? The factorial means 3 times 2 times 1. So I already had a 2 there. You got an extra 3. Now you got 3 times 2. Right. All right, so now we're going to just keep going. We're going to get the cubic approximation. We're going to get the 4th degree approximation, the 5th, and the nth degree approximation. And we just keep doing the same thing. Right? We're saying, all right, let's integrate by parts. So this is u is the third derivative of f, and whatever's left, the x minus t squared over 2 dt, that's the dv. Take the derivative here to get the 4th derivative of f. Take the integral right there to get, again, the minus sign pops out because of the u substitution with the minus in front of the t there. And the squared becomes a cubed over 3. You already had a 2 in the denominator, so you end up with a 3 times 2, which is a 3 factorial there. And doing the same things, right? This was already there. You've got u times v right here, evaluated between t equals b and t equals x, minus the integral of v du. Plug in the x, you're going to get a 0. Sorry, plug in for t. Plug the b in, you get x minus b cubed, but it's minus minus, which becomes plus. So there's that term now. Plus this integral here, again, the minus minus becomes a plus. So now we've got the cubic approximation being all this stuff right here, plus the stuff that's going to be not covered by that approximation, which means it's the error in order to make it actually equal to f. And so that error can be, we get a handle on how big that error is if we knew how big the 4th derivative might be. Treat that as a constant, pull it out, integrate that stuff. That's going to turn into a cubed over, so it's going to be a 4th over 4. So now you're going to have a 4 in the denominator as well as the 3 and the 2 that were already there. So you got a 4 factorial. The x minus b becomes an x minus, sorry, the cube becomes a 4th. So you get this thing where m is an upper bound on the 4th derivative, right? Dot, dot, dot. Just keep doing the same thing again. Integrate by parts. Get your 5th order. Get your 6th order. In general, it looks like this. The result is you got f of b, f prime of b times x minus b, the second derivative, x minus b squared over 2, and so on and so forth. The nth term, so the nth degree polynomial, Taylor polynomial, would end right here with the nth derivative of f evaluated to b times x minus b to the n power divided by n factorial. Right? N factorial would be 1 times 2 times 3 times 4 all the way up to n. And then this part is not part of the Taylor polynomial. This is where the error comes from. This is the part that's not accounted for by the rest of this. Right? And so if I got a handle on how big this could be, so if I just knew how big the n plus first derivative could be on that interval between x and b, treat it as a constant. I know this integral is going to be less than that. So I pull that out, and then you can just integrate this thing. The n is going to go up to an n plus 1. You're going to divide by n plus 1, so you're going to have an n plus 1 factorial on the bottom. And you're going to have an x minus b to the n plus 1 on the top. Right? This is the Taylor polynomial of degree n, and the associated error all comes out of this process. Just keep integrating by parts and seeing what happens. Right? So there you go. I think in the next video I will show you another way to come up with this. This was stuff as a student. I don't remember doing this integration by parts thing. They probably taught it to me. I didn't pay attention as much. I didn't like this stuff as a student. I have a different view of it now. I very much like it, and I can see patterns. I can understand why we're doing this. anyway, yeah. But we'll look at another way of generating this in the next video.